All right, today we're going over the last two parts of diagnosing our models. If we remember, step one is, do the slope coefficients make sense? Do the coefficients make sense? Are they the way that we expect them? On the homework, we did one of them where we're estimating wages. And one of our coefficients didn't make sense, right? The coefficient on age was negative. Remember that? The coefficient on age was like negative 0.11, which would indicate the older workers get, the less they make. And that doesn't make sense. Usually your income goes up as you get older. Thank goodness. So, that didn't make sense. That's what the book was trying to get you to identify. Step one is, do my coefficients make sense? Step two is, what is the standard error of the regression, especially as compared to the dependent variable? Step three is, we interpret our adjusted R squared. Step four, we look to see if our individual variables are significant. We look to see if individual variables are significant. We look at each variable and its t-stat and its p-value. We compare its p-value to a given value that we've come up with, and we ask if our variables are significant or if they need to be dropped, if we need to alter our model. Fifth, we look to see if our independent variables are correlated with each other. We look to see if we have multicollinearity. Multicollinearity. And in chapter 15, we see assumptions of our model. Assumptions that have to hold for an OLS, ordinary least squares model, to be valid. Number one, the model is linear in function. So we talked about this. This is a linear model. It is a linear model. I want to jump to 3. 3, there is no exact linear relationship between the values. This is what we looked at on Monday, multicollinearity. And I'll go through examples of how we look for this and test it. So the example I gave was, if we're estimating home prices, and we're looking at, okay, the home, we do square feet, number of bedrooms, number of bathrooms, miles from the ocean, because in Florida, closer to the ocean, the higher the real estate, miles from the ocean, and how many blocks is it to the nearest beach? Well, miles to the ocean and blocks to the beach are going to be very strongly related. Very strongly related. So those two are they're essentially the same variable. And when that happens, we have multicollinearity. This is a great day for vocabulary. You get these words on, start using these words, throw them around work or something. Oh, points. Points. It's almost as if you too had a nice bow tie on. By the way, guys, when you get that professional job, 1 day a week, wear a tie. If it's not required, 1 day a week, put a tie on. Why? Because then they can never tell when you're interviewing. And they can never tell when you're out looking for the next job. 1 day a week, put the tie on. It won't hurt you. Every now and then, people ask, what's the tie for? Oh, I got a meeting later. Don't worry about it. Just let them wonder where you're interviewing. Today I want to talk about number 2. The expected error is 0. Now I know they throw a lot of weird math in here. Conditional on x to xk values, the expected error, thus this equals this. Okay. The expected error is 0. We say that the variance of the error term, E, is the same for all values. Otherwise, if the variance is the same, it's homoscedasticity. The variance is the same variance, homoscedasticity. If it's not the same, we have heteroscedasticity, which is a problem with our models. The error term is uncorrelated across observations, otherwise we have serial correlation. The error term is not correlated with any of our predictors. The error term is normally distributed. So you notice that a lot of these assumptions are about the error term. So let's talk a little bit about what this error term is. Remember, our model is this. What we're predicting is a function of an intercept plus a coefficient times one variable plus a coefficient times another variable plus some random bit of error. So when we estimate this, we come up with an estimated value, our y hat, which is our beta 0 plus beta 1x1 plus beta 2x2. And this is what we estimate. But our estimates are always off by a bit. We don't have perfect models. The map is not the territory. All of our models are in some way flawed. Remember on the test when we estimated the points per minute for the players on bonus? On the test, we estimated points per minute. We're up here, points and minutes that they played, and the players had things like this. The one guy was way out here. And we had something that looked like that, right? And we built a model and drew a regression line through here. This is our estimate. This is our y hat, our best estimate of these. But we know that these points are our real data points. And if we want to estimate, for instance, a person who has this many minutes, we can go up and find our point, and that's our estimate. Is our estimate going to be perfect? No, we don't think it's going to be perfect. We think it's going to be statistically valid. But notice that our actual points are not on our line. If we were to guess this point here, if we were to try to guess this point here, given a certain minutes and a certain points, what would our guess be? Our guess would be where this hits on our line, if we're trying to estimate points by minutes, which is what we're doing. So our guess for this point would be here. That's where our model would predict. However, this is what we really measured. The difference between whatever this value is, the difference between reality and our model is our error term. It's how much we're off by. In statistics, we call it a residual. We call our error term, how much our estimate, our model is off by, a residual. So if there are 18 data points, how many residuals do we have? We have 18. We have one for each data point. For some of them, our estimate is too low. So up here, the reality is higher than our model. And in that case, our residuals are going to be negative. In some cases, we overestimate. And in that case, our residual is going to be positive. If we get a model that looks something like this, where here's our regression line, and here's all our data points. Not a very good model, right? We could make this model better by readjusting it and shifting it down this way, clearly. But if that were our model, we're consistently overestimating, right? If this is our model, we're consistently overestimating. Likewise, if this is our model, we're consistently underestimating. So we don't want to be consistently over or underestimating. We don't want to be consistently over or underestimating. If that's the case, there should be as many above as below. There should be about as many that we're overestimating as we're underestimating. As a matter of fact, if we were to add all these up, what would the average of our error terms roughly be? If we're overestimating as much as we're underestimating, and some of them are positive and some are negative, we would expect the average of our error terms to be close to 0. So this is a test we can do to see if our model is good, to make sure we're not consistently overestimating or consistently underestimating. Another thing we can do is we can graph the residuals. For instance, here we miss by, say, 3. We're under 3. Here we're under 3. Here we're under 1, under 1, under 1, plus 3, plus 2. So we can go through and graph these. We can graph them around a 0, where these are positive and these are negative. And we can look at where our error terms fall. Some we miss under by a lot, some we miss over by a lot, some are pretty close. We can graph our individual error terms. And what we assume, if our model is good, I'll go back a slide, we assume that the expected error is 0, that the average of our error terms is 0. We assume that our error terms don't have any particular patterns, that they're not heteroscedastic. I'll show you what that looks like in a bit. We want this to look like this. What's the pattern here? Say it. Say it. You're right. There is no pattern here. Is it a positive relationship? No. Negative relationship? No. It's that shotgun blast pattern, that everywhere. This is the type of residual plot we want to see. There should be no pattern whatsoever to our residuals. No correlation, not with a predictor, not with anything. It should be normally distributed with an average of 0. So we're going to look at what that means. But given that, number 6, we've already covered 1 through 5. Number 6 in diagnosing our models is residuals are normally distributed. Your residuals, your error terms, should be normally distributed. What does it mean to be normally distributed? That they fit along a bell curve. That they fit along a bell curve like this, average of 0, some positive, some negative. Ones that we miss by a whole lot, there shouldn't be as many of them. Ones that we miss by a whole lot on the negative, there shouldn't be a lot of them. Ones right around 0, we should have a lot more small misses than we have large misses. So our error terms should be normally distributed. We should see a lot more here close to our line of 0 than far away. That's number 6. Finally, number 7, the last step in diagnosing our models. Your residuals do not show a consistent pattern. What do I mean by a consistent pattern? I keep slowly moving markers to the desk, which is the least useful place for them. It's like the people who put the remote control on the TV. Right? And I don't get it. You're forcing me to get up and walk to the TV anyway. You've eliminated the purpose of the remote control. Silly. So do you have your heads down right now? Like, around our line of 0, there should be no consistent pattern to your error terms. If we have error terms that look, I've already used red and blue. Is there a pattern here? Yes, there's a very distinct pattern here. Is there a pattern here? No. Pattern? No pattern. This pattern is the distinct telltale. This trumpet shape is the distinct hallmark of heteroskedasticity. Heteroskedasticity. What this is saying is as we go along, we keep missing by more and more. It can go in either direction. It can go like this, or it can go this way, where your errors can converge. But that sort of trumpet shape is a telltale sign of heteroskedasticity. We diagnose it by looking at a graph of our error terms. I will get into heteroskedasticity more in a bit. Your error terms should not look like trying to make them look random. Pattern? Definitely. This is the telltale pattern of serial correlation. Serial correlation. This says that your error term is correlated with a variable. This is the telltale pattern of serial correlation. So instead of going through all these patterns and saying, look for this one and this one and this one and this one and this one, number 7 is your error term should have no pattern whatsoever. There should not be something distinguishing. They should look like the shotgun blast scatter shot. Checking these assumptions. How do we do it? The true error terms cannot exist. However, we can look at the residuals, the difference between our y that we actually observe and our y hat that we estimate. We can look at that. It is common to plot the residuals on the vertical axis and an explanatory on the horizontal axis. So we might look at our residuals for each one. When estimating a regression in Excel, the dialog box that opens after when you get to your regression allows you to select residuals and residual plots. So when we run our regression, we can turn this on in Excel to look at them. Excel provides that as an option because it is so commonly used. It is a basic, fundamental step in diagnosing your model. What do we do? Our model suffers from collinearity. It violates number 5. Our models are correlated with each other. Remember we said that a sample correlation greater than 80 in either direction is bad. What do? Drop one of them. Remember we see the very high R squared? When two of our variables are highly correlated, your R squared shoots up to 99% mathematically. Drop one. Remedying multicollinearity. A good remedy is to simply drop one of the variables. Increase your sample size, and maybe those two variables will separate, maybe they won't. You can transform the variables, which it teaches you to do in Chapter 17. It almost never makes sense to do nothing here. Almost never makes sense to do nothing. Typically what we do is just dump one. Common violation number 2, the error term is heteroscedastic. Residual plots to test for heteroscedasticity. So here we see that. Remember, as a standard, we plot an explanatory variable on the horizontal, like square footage, and the residual on the vertical, centered around 0. So this graph is telling us that our model is very good for small homes, but the larger the home gets, our model just isn't as good. This is very common. Very, very common problem. And we can fix it. Very common problem. This comes into play a lot more when we do time series, when this is a date, when we find out that we're very good at estimating things in the past, but as we move forward in time, our estimates get bad. Very common. What do we do about it? It results in inefficient estimates. So we have to correct our standard errors. We use what's called White's standard error. We can also run a statistical test called White's test to numerically test for heteroscedasticity. And we'll learn how to do that too. We can run White's test. Many statistical packages have this option available. It should say every statistical package has this option available. The current version of Excel does not. Why not? Because Excel is not a statistical package. It is an office spreadsheet. So if you have heteroscedasticity in your model, Excel, there's nothing you can do about it. Common violation number 3, the one I have over here. Gosh, my picture looks like their picture. The error term is serially correlated. This again comes into play in time series data. Over time we see changes. We see this with seasonal data a lot, if you're not correcting seasonal data. Like if you're looking at employment, employment naturally goes up a lot in the summer, then falls in the winter, then goes back up in the summer. Employment is very cyclical. So you have to correct for that. And if you don't correct for that, sometimes you get this type of pattern, and you have to correct to it. Again, remedies are not easily accessible using Excel. Thank you, book. Variable is endogenous. This commonly occurs if you're admitting an important explanatory variable. I love when the book goes into this one too. Unfortunately, endogeneity is difficult to fix. So the book just basically passes the buck here. This is difficult to fix and says, further discussion of these types of variables is beyond the scope of this day. It's another way of saying you're on your own there, Skippy. Right? All right, it's a very complex, and once you have endogenous variables, you get into some deep math, and it's a complicated interpretation. So there's a semester on this in grad school. So, complicated. Questions? We have completed our 7 diagnostics for our models. We have shown our 7 steps in diagnosing our models. Take that page and frame it. Because on your projects and such, I will look for you to apply these 7 steps to your models. And as you apply them, what you do is you build your model and you think, okay, this looks good. I think I've got a good model on our hands. Well, how do you know? Well, my coefficients look good. They're all the right direction. They seem to make sense. My standard error is relatively small compared to my dependent variable. My R squared is good. Now we're 3 into 7. This looks good. Let's make sure everything's all right. All our variables are significant. Okay. Run through the test. Look at my residuals. Residuals look good. I think I've got a good model. Let's put it in the paper. Let's start writing. All right. That's what we do. We run through this with our variables. So you want to do some examples? Outstanding. I'm going to open my Gretel. And we already did baseball, didn't we? Let's do crime. Because I looked up what it is. So let's do crime. It's in chapter 15's data, I believe. I'm going to alter mine a little bit up here. I'm going to delete the names of the cities because I don't care. And I'm going to use this just like it is here. I've changed my headings to make them more readable. This is the violent crime rate. This is the poverty rate, the median income, population under 18, population over 65. These are percentages. So all of them are percentages except for median income, which is in thousands. You don't have to change yours if you don't want. I just want to make them more readable for my example up here. So I have my data. Gretel, open data in a user file. Found one valid sheet, 5 variables, and 41 observations. That's good. I see that I have 1, 2, 3, 4, 5 variables up here. The light bulb is the good sign in Gretel, so we're okay with that. Do I want to give it a time series interpretation? Nope, not yet. So now we're ready to begin modeling. Now, we should look at our summary statistics. We should look at our averages. We should make sure our data is linear. We've already done all that good stuff, right? Sweet. Time to start modeling. Just reminding you, you should do all that before you click the little beta button down here and start doing your thing. What are we trying to predict? Violent crime rate. What are we predicting it based on? Everything we can throw on it. So we throw that in and we get our model. Now it's time to run through the 7 steps. Do the slope coefficients make sense? So we're predicting which city has more violent crime. We're predicting a violent crime rate. As far as violent crime goes, what's better, higher or lower? Lower. Less crime is better. So, poverty rate. What would we expect, given pictures we look at on Facebook, which is where we get our economic and policy data these days? What would we expect the crime rate and poverty directionally to be? Positive, right? More poverty, more crime. That's what we see. That's true. Median income, what would we think? Higher the median income, maybe the lower the crime. So a negative relationship, what do we see? Well, we don't see that. Population under 18, well, those are criminals. So we'd expect the more kids, the more crime, positive. And that's what we see. Population over 65, do the elderly commit many crimes? Not a lot. So we'd expect that to be a negative relationship, and yet it's positive here. So we might have some problems with our model, right? Number one, we already know we've got issues. But let's keep going. Step number 2, look at our standard error. Here's the standard error of our regression, 339. Seems radically high for a poverty rate. So some things are going on here. Interpret our adjusted R squared, 40. Not bad, but a really high R squared isn't going to help you at all if you can't explain why these are the way they are. So that R squared, this is why I say do not fall in love with your R squared. You can look at this model and say, I have a 40 R squared, we're good, publish, let's move on. No, you have serious problems here. What you're telling me is that if we want more crime, what we need is, or if we want less crime, what we need is less kids, or more kids. So your model doesn't make sense here. So do not fall in love with your R squared. Don't run your model, go straight to your R squared and go, it's high, we're good, moving on. Bad idea. Number 4, are all of our, this is difficult, are all of our variables significant? So we want to look to see if our variables are significant. Gretel and Excel very conveniently run a hypothesis test for us, where the null hypothesis is that the variable is not significant. It is 0. It is a bad variable. The alternative hypothesis is that it is a good variable. We know that if the p on this hypothesis test is low, the null must go. So if the p-value is low, we throw out the idea that it's a bad variable and accept that it's probably a good variable. So we want the p-value to be low, right? How low is low? Well, it's really good. It's really good. 3 check marks if it's below 0.01. It's pretty good. 2 check marks if your p-value is below 0.05 and you're significant at the 95% level. And it's still okay, 1 check mark, if your p-value is below the 10% level. Really good So let's look at our p-values. We never interpret the p-value on the constant. We don't care. Poverty rate, 0.0046. Low? Yeah, pretty low. Pretty good. Median income, 0.5. Ooh. Population under 18, 0.8. Radically bad. Population over 65, 0.61. Awful. But this one variable is very, very good, right? It's significant at the 0.01% level. It's very, very good. It gets 3 check marks. Or in Gretel, it very conveniently gives it 3 stars. Gretel will put 3 stars out here for a variable that's significant at the 1% level. It will put 2 stars next to a variable that's significant at the 5% level. And it will put 1 star next to a variable that's still significant at the 10% level. Gretel was nice to us that way. There's never a bad time to show an XKCD cartoon. So here's our p-value and interpretation. Very low p-values, highly significant variables. Still under 0.5, significant. Right at 0.5, crap, do it again. See if you can push it lower a little bit. When you read papers, you read these weird, you read things that are trying to say that it almost counts. Highly suggestive, on the edge of significant, nearly significant, son of significant, revenge of significant, significant for, age of significant. You know, they've said they're going to come out with 4 more Transformers movies. Oh my God, shoot me in the face now. Aren't they just getting worse and worse and worse?
The last one.
I thought getting rid of Megan Fox would make them better, because getting rid of Megan Fox typically makes everything better. But it just, no. They just get like worse and worse. I don't know how you can squeeze 4 more out of that dying corpse of a franchise. It's time for a reboot. So, put the cartoon up. Gretel very conveniently adds the stars out here to show you how significant your variables are. So we know we need to fix this model. How do we fix this model? How do we go about making this into something that we can believe in? Well, let's look at our variables one at a time. We've talked about diagnosing our models. Now let me go through examples of fixing them. We've diagnosed our problems. Let's fix them. First of all, this population under 18 that has an 85% p-value, that doesn't look useful at all. That looks bad. So let's drop that variable. So in Gretel, what I'm going to do is go to Tests and Omit Variables. Tests and Omit Variables. And it says, which one do I want to omit? I like this in Gretel because I can drag this around and look over here and see which one. I can go back and look at this, and it estimates the reduced model. So it'll take my variable once I remove population under 18, and I click OK. It runs a second model down here. So now I can put them side by side and compare them. So let's run through our steps again. Some of these still don't seem to make sense. Our adjusted R squared has increased a little, and our standard error has decreased a little. Both of those are good. When we look at our p-values, we still see that a couple of these are really high. So while this model is better, it still doesn't look good. So who's the next to go? Who gets voted off the island? Yes. As in every good case, we should eliminate the elderly, says the oldest man in the room. So now we'll do the same thing. Test, omit variables. Population over 65, we run that. Once again, our R squared has increased a little. Our standard error has decreased a little. This poverty rate keeps getting more and more significant. You notice that? As we eliminate unwanted variables, we were at 0.004, now we're down to 14, now we're down to 6. This keeps getting more and more significant. But still, this median income just doesn't seem to be that good. What might be a problem here? Could be small sample size. We notice up here that we have 41 observations. So 41 is not a huge number, but it's statistically valid. What is the poverty rate? Come on, it's still an econ class. What is the poverty rate? What does it mean to be in poverty?
It's less than $20,000 a year.
But it's based on your what?
Income.
What might we want to look for with a two? Both of these variables relate to what? How much money you make. Might these two variables be very highly correlated? That's a possibility. We may have multicollinearity. We may have multicollinearity, step 5, if we got that far. What we do know is that median income isn't working for us, and we need to eliminate it. Here we have this model. R squared is higher, standard error is lower, all of our variables are significant and in the direction we would think. We can't have multicollinearity because we've omitted everybody else. What's it time to do now? Residual, step 6. In Gretel, very easy to do. We take our model we're looking at, analysis, display actual, fitted, and residual. And it gives them to us numerically. Here's the actual, here's what our estimate would be, here's the residual. So we can look at them numerically. At the bottom are some statistics on them. Our average error is negative 1.7 to the negative 14. A tiny, tiny number, right? Because our error is supposed to be an average of 0. Is that pretty close to 0? Pretty close to 0. We can graph them. Where in Gretel do we find graphs? Well, to the surprise of no one, we would click on graphs, residual plots, and remember our residual plot by standard has an explanatory variable and the residual error on the vertical term. So we might plot them against poverty rate, which is our last existing explanatory variable. Here's our residual plot. Is there a pattern here? Absolutely. Our data is heteroscedastic. We estimate pretty well when the poverty rate is low. But for poor communities, when the poverty rate gets very high, we missed by a lot. So we have probably a bad model here that would need to be corrected. Everybody see how we did that? You can play around with the graphs in here. You can go to graphs and look at, for instance, actual versus fitted. And here's the line where they should be. And here's your predicted and here's your actual. You can look at things like this and see how close you are. You can look at by observation number, see how you're missing. Let me show you this too. I'm going to back all the way up. I'm going to close these out. Go back to our original model. And let's say at this point we suspect multicollinearity. We suspect that some of our variables are correlated with each other. So what we want to do is find out if any of these are correlated with each other. So we could go to Excel and run a lot of equals CORREL, equals Correl statements, right? Find out if poverty is correlated with income, if poverty is correlated with population, if elderly is correlated with youth, if elderly is correlated with median income. We have to run a lot of them, right? A statistics package like Gretel, if you go to test and collinearity, test and collinearity, we'll run tests for this. This is the VIF. This isn't the one I wanted. Let's see. Tests. No, I know it's in here somewhere. I had it last night. Here, analysis. This is a way to do it. Tests collinearity, does a VIF test, variance inflation factors, that does very complicated statistical analysis to see if you have exact collinearity. This is, as the slides say, beyond the scope of this course. But it basically runs this equation to look for multiple correlations. Instead, what we're going to do is analysis and coefficient covariant matrix. Damn, that's not it either. That's the covariance. Where's the correlation matrix? Am I missing a correlation matrix somewhere? Oh, okay, I got it, sorry. We have to jump back to our data over here. We don't do it in the model, we do it in the data. I'm sorry about that. I lose my mind sometimes. Aren't we glad we got that on the video? We do it over here from our data, and we highlight the ones we want using your Shift key or your Control key. In Windows, Shift, holding on Shift and clicking selects everything. Control selects them one at a time. Go through these at home and look at things like in Tools, Data, View, Add. Look at some of these things and play around. You're not going to break Gretel, so what we do to get the correlation matrix is View Correlation Matrix. View a correlation matrix, and it asks which ones we want to include, and here it gives us a correlation matrix. See that you have that popping up over here on your student's file. So how do we read this? poverty rate is correlated with poverty rate at 1. They're perfectly correlated, they're the same variable. They have a perfect correlation, or identical. But remember we said poverty might be correlated with median income? And it turns out, in fact, that it is. Strongly negatively correlated. This is no surprise. The higher the median incomes, the lower the poverty rate. As seeing that this is above an absolute value of 0.8, we should know that we can only use one or the other of these. That'll end it right there. So now we can look through here and look for relatively high variables that might have a problem. If you have a very old population with a lot of people over 65, it's difficult to also have a very young population, right? So if we look at the correlation between those two variables, we see that it's pretty high. 0.48 is pretty high. I mean, it's not a killer, but it's something we might want to take note of. So Gretel lets you run this correlation matrix very easily and look at these quickly and run the test for number 5 in our steps for diagnosing our matrix. There is no equivalent thing in Excel. Questions on the correlation matrix? I'll show you again how we do it because I screwed it up. We've imported our data. Maybe what we want to do before we even start modeling is grab all of our variables, view correlation matrix. Another neat one you can do is you can highlight all your variables and do view summary statistics. Where now for everything it shows us the mean or the average, the median, the minimum, the maximum, standard deviation, skewness. Here's all your averages and everything right here. Copy those out and drop them right into your paper. Quick and easy. Here's a summary of my data. Absolutely no reason not to have this in your data. You were looking at JCPS and school data. What else were you looking at? You got it by zip code, right?
Yeah, and I went based on zip code and the list of schools that's in the area.
So we might want to look at median income for those zip codes, because some zip codes in Louisville have very high incomes, and some zip codes in Louisville have very low incomes. And I might ask myself, if I read this paper, if we're talking about income, what's the median income? What's the average? What's the highest? What's the lowest? How do these vary? Do they even change a lot? So, good information that should be included in a paper. Raymond, this is killing me today.
What?
It's just killing me. I went to the barber yesterday and shaved off most of the length. I took off effectively all the length on my face yesterday. I'm left with this stupid little stubble. And all day long I've been at work and in meetings and things like, that's, no. It's just killing me today. You wouldn't think that it's weird, but once you bring it down, once you change it, it'll change your whole life. Shocking. Summary statistics, correlation matrix. Let me show you this one too in Gretel. I like this one, where we can go down here and do our model. And we've already decided some of these variables are bad, right? Did you see the steps I went through where I slowly eliminated one variable at a time until they were significant? Gretel is a tool that knows that, and where I was doing test omit variables, I can tell it down here, sequentially eliminate variables unless they're significant at the 0.1 level. I can tell it to sequentially eliminate variables. Drop the worst one. Look at your test. Are they all better? Nope. Drop the worst one. Are they all better? Nope. Drop the worst one. It'll drop off one variable at a time until it gets to the point where they're all significant at the 10% level, which you can select. See how it just takes us right there? This is where we wound up, right? In other statistical package, this is called a stepwise regression. A stepwise regression, where you step by step eliminate one variable at a time. Over here, again, graphs, residual plots. We can look for our patterns. Which of these looks better? Clear heteroscedasticity. This one looks a lot more random. It still looks heteroscedastic, sort of going this way. You still see that trumpet. Many of you put Gretel graphs in your homework. Much appreciated. Questions on any of this? Diagnosing your models, looking at your variables, looking at your error terms, your residuals, diagnosing and fixing your problems. This is a big step of what we'll be doing going forward, is diagnosing these types of problems. Next week, on Monday, I'm going to start on non-linear models. Everything we've been doing so far is linear. Next week, we will get quadratic. We will get logarithmic. We'll get polynomial. We'll learn to transform variables and deal with the non-linear world.